Hello and welcome to YMT217 Programming Languages. Today we are discussing the second part of evolution of the major programming languages, which is this chapter 2. Previously we discussed different topics about programming language itself, and we explained how it was really hard to program at early stages of computing or computation development. Why? Because in brief, programmers had to write their own translation of whatever they coded back then. So they needed a way to translate it, and that was manually done in a similar way to assembly now. And we explained how that went for some time until today. We will discuss the other milestone in the development of programming languages. We will speak about the relationship between IBM 704 and Fortran, and we will explain about Lisp as a functional programming, which actually opened the way for many other development. These two I would call, or many other also would call them, you can say, the kickstart of real high-level languages or programming languages. All right. This is like a schematic for the whole development of programming languages. More or less, there are other also programming languages. However, we are trying to bind with those as real key in the milestone of programming languages until our today's development. All right. You don't have to memorize anything here. It's just for your info only. We will discuss most of those, by the way. But for today, we will just go through Fortran and Lisp because they are really important and give you an idea how they were developed and in which context. Again, the idea of programming language in high level or in a high level way needed a translator. A translator means what? We need to go from our level, human being level, the level we understand, the language that the language that we speak and communicate with, and go to the level of the computer, a low level that understands only ones and zeros. So we need a translation process, a process that translates the program or the code that we write to a code that the machine understands. Good. What kind of a purpose are you going to write the code for? Because now our purpose is totally different, not exactly like back then, back in time. Back in time, computers were extremely slow and efficient. Their memory or whatever design memory for them was really limited. Their processors were extremely primitive. So programming back then is not exactly like programming now. So what are we speaking about now is exactly the primitive time of programming language. So when we speak about IBM 704, go and check its specifications. You wouldn't even believe that they could even program with a programming language such a machine. We can't compare it to the machines that we have now, although the same concept applies, but it was an extremely primitive machine. Well, they thought of an idea to program with it. So there was a smart guy called John Backus, and this guy led a group at IBM for developing a programming language actually for mathematical use, again scientific calculation, for IBM 704. So they came up with the idea of Fortran. Fortran means what? It's mathematics, so it's about mathematical formula translating system, Fortran. Initially it was written by this capitalized letters or capital letters, and they invented the first Fortran 0, and it was in 1954. This Fortran 0 was never implemented. They just set up its rules or description or whatever. They published a paper about that, but they never implemented it. Next to that, what happened? The same team strived hard to come up with an implementation, so they came up with a new version of Fortran. They called it Fortran 1. And for Fortran 1, they did what? Actually, one of the main ideas made them to come up with the idea of Fortran is the difficulty of dealing with floating point in hardware. Hardware back then, as I said, IBM 704 was not fit for floating point. So they needed a software to simulate the process of floating point. They could come up with the idea, or you can say the guideline in Fortran 0, then they improved that Fortran 0 for an implemented version. They called it Fortran 1. Well, this Fortran 1 is compiled, so they could compile a programming language code to come to machine code, or to be translated to a machine code. All right, that's good. So they could solve somehow a floating point problem with no machine relevant solution. But it was not that much mature. Fortran 1 was not really that much mature. It set up the whole idea of Fortran itself after the guideline provided for Fortran 0. Let's just look at the context Fortran 1 came in. Computers were extremely inefficient or unreliable, small in memory. The processing speed was extremely slow compared to today. The application for scientific use were extremely popular. They needed some programming ability to calculate scientific things back then. So they were desperate for some machines like that. By the way, Fortran itself had no exact programming context nearby it. All programming languages back then were extremely primitive. So there was no exact competitor to Fortran back then. That was also a problem. One more thing, how much our machine could take. So if we write a program in like 100, 200 lines, 400 lines, how about 1,000 lines? Can it take it? That also was a major problem. The features of Fortran 1, there was no dynamic storage at runtime, assigning a storage or a memory at runtime while we are running. Okay, in brief, this is not exactly the correct sentence, but while we are running the program, I can say conventionally, there must be a memory to be assigned to the program. There was no such a need. There was no need for arrays, also loops. There was no string handling functionality, no decimal, arithmetic, or powerful input and output. That was extremely primitive if you think about it. That's not enough. That was not enough. So the basic idea was like this. How about having a programming language that runs with a little bit of looping, formatted input and output? How about user-defined sub-programs? How about maybe selection and so on? So this came actually as Fortran 1 instead of Fortran 0, actually the earlier version, okay? The earlier version. This one was, you can say, a dramatical movement in Fortran. And data typing, by the way, there was only implicit data typing. Data typing means what? If you want to create an integer, let's say, declare for an integer data type, you need to use I, j, k, l, m, and n at the beginning of the named variable. Okay, so let's say you want to call a number num, n-u-m, you need to start by n. In this case, it will be considered implicitly as an integer. If you do not start by I, j, k, l, m, n, then it will be considered a floating point number. That was the implicit way of declaration. Well, but still it had all these, the selection also statement of f else, three-way, f then else. Data typing, as I said, only implicitly was available. All right. That was the basic idea of Fortran 1. Alright, now, which machine we use? Again, we said about the IBM 704, and I really call upon you to go and check its specifications to understand what I'm saying now. The problem with this machine, it was really limited. So if you write large programs in Fortran 1, what happens if you try to compile them? Most likely they fail, because of the reliability of the 704 machine. That was a problem. The machine was the problem, not exactly the code. It was designed for actually machine-specific language. It was not versatile. It wasn't running in any machine. Computers were not that much popular back then, and software packages or programming languages were designed for specific machines, because if every team or these teams were running their software for their own machines, not for everybody. Back then it wasn't exactly versatile like now, adaptable or portable based on the operating systems and the hardware machine that we have. Okay, one more thing, the code itself was really fast. Realized also the team designed this programming language, realized the capacity of how fast it is, but the problem with the machine didn't exactly help them to run or to code efficiently. But the concept itself was successful, and because of that it became popular. That was a key point for Fortran 1 to succeed or to become widely spread. It solved different issues, so people adopted it. Alright, now the idea is like this. It took time. One of the major issues was in Fortran 1 to come up with a final version of it. It took around 18 years. That was really a problem. Of course, time matters in this case, but it solved so many problems to the point that it became really widespread. So the Fortran 1 was popular back then. A lot of people thought of, how about if we contribute to its development? Again, a new system came, Fortran 2 instead of Fortran 1, now Fortran 2. It solved a lot of the bug problems that were available in Fortran 1. Also, it's still an initial version of Fortran. The first actually implemented version, because Fortran 0 was never implemented, so they couldn't exactly debug its errors. Now Fortran 2 started debugging errors in Fortran 1 and also brought to some additions like the subroutines, the compilation of subroutines. Now instead of recompiling the whole program, you could just compile a few subroutines to be added. That helped in enlarging the possibility of programs. That means before we were limited to less than 400 lines or so. Now it became much more than that, based on like a subroutine addition of compilation. All right. Now there is something we call Fortran 3. There is a version for Fortran 3, but it was extremely limited. Why? It didn't take much time to become popular. This is number one. Number two, Fortran 4 came quickly as a standard. Fortran 4 came right after Fortran 3, but it became the standard back then in '66. It was the ANSI standard. Anything standardized, like the way we use in our reality today, we use standardized things back then also. This was a standard version. People used it. Fortran 3 didn't have a chance. So it went directly to Fortran 4 and became also widely adopted by many teams and programming teams. It solved different issues. The first one is the explicit declaration. We said that about the IJKLM for integer. Now no, you could, by Fortran 4, you could do the explicit declaration for integer or float or whatever. Also the logical selection statement came to use. Subprograms also could be used as parameters, so we can send the whole subprogram to a function. That's also possible, right? That became a milestone in Fortran itself. Also in Fortran 4, the name Fortran, which was initially used as capitalized letter, became in lowercase like this. Why? Because of the change in the way Fortran variables were written. It was obligated back then to use the capital letters for everything you write in Fortran, but with 4 now the whole idea changed. All right, how about 77? This is actually you can say the first step in the final versions that we have now. Not the final, this is the first step for the final versions that we have, the versions that we have today. It became the standard. This is a standard in 78, okay? Again, like the standard that we used here, this is another standard around 10 years later, 1 decade or more later. A few improvement like the character string handling. This one did not exactly have the character string handling. Again, Fortran 77 became popular as a standard. and solve different issues, but this was not the final improvement in Fortran itself as a language. Fortran 90 came to existence and it added a lot of things like modules, dynamic arrays, pointers, recursion, case statement, parameter type checking, and these are extremely needed for modern day programming. So you see the improvement added or was added to 77. Well, back then they were not exactly needed. Neither do the machines have the ability. Neither did the machines back then have the ability to process these things, or at least most of them. All right. Now Fortran 95, this was the one available during our time, actually early 2000 when we started coding things. It was also popular back then. It just did a minor actually change of Fortran 90, some additions like for all as a loop. This is a more extensive loop construct for iteration, some deletion of problems in Fortran 90, but no major thing actually. Fortran 2003 is exactly the same model of 95, but it added the support of object-oriented programming. That's very important. Plus also procedure pointers, not just normal pointer, and also the interoperation with other languages like C. So it could have like interoperation with some other languages. That is also a contribution and was needed at the beginning of 2000. There was a demand for such thing. Fortran 2008 did not actually contribute much. It added only specific things like local scopes, blocks of local scopes, co-arrays. We will speak about these later on, not now. Also some looping type or some iterative capabilities, like here in this case for all, here do concurrent. As you see, from 95 onward, only you can say problem-specific things were added to Fortran versions, and that is what we have nowadays. We don't have a dramatical change in programming languages in the orientation they work. We have only problem-specific things that they are added as just a solution with the programming language itself. All right, how about the evaluation of Fortran language? I would tell you, anyone who knows programming, if you say about Fortran, he would tell you this is the main programming language, that high level, of course, that encouraged other programming language to come forward. So basically, this programming language was one of the main programming languages back in the day, and it helped in developing the concept of programming language with the translation or compilation process for many other programming languages. Now, the idea is it was really highly optimized. And as I said, they took 18 years to come up with the idea they were developing, even to the point that their software, which is the programming language compiler itself, or the implementation of the language itself, took them a further step from the available machines. Machines could not exactly run properly with the available capability of the programming language. So it took time until machines were developed further to realize the powerful or the power, actually, not the powerful, the power of Fortran itself. All right. Runtime was really good, optimized. It was quick. It made, as I said, dramatical change in the way we look at programming language, as also the way we use even computers. Computers also try to catch up with Fortran back in the day. All right. The second type of programming back in the day that encouraged programming language to come to a new step or to a new milestone in the industry of programming languages is functional programming. Functional programming we speak about, as I said in the beginning of our explanation about programming languages, we said we have different paradigms, the way we look at the programming language or the use for the programming language itself. Now for functional programming, we look for different things. We are not interested much in the imperative way of running things. We are rather interested in processing things using functions. A function with a parameter. We pass a parameter to it, or an argument in this case, and we get an output. We don't write procedures and so on and so forth. It depends on the paradigm you are looking for, or the way you look for doing things using this programming language. All right. The concept itself was developed by Alan Shaw and Herbert Simon at Rand Corporation. Rand itself had its own computer. The computer was called JONIAC. It was named after the combination of John von Neumann, so John, J-O, then H, Neumann, N, so John from John and N from Neumann. NIAC, numerical integrator and automatic computer. So it was one version of the computers back then, and for it they created, or they developed, something they called information processing language, and they gave it version 1, IPL 1. It was not implemented. The second version was implemented on the JONIAC computer, Rand computer. Okay. Now, next to that, it was also again an initial version. It was like somehow a drafting way for programming language. Although it was implemented, they came up with other versions until actually IPL 5. IPL 5, all these versions until then, they were somehow low level, like assembly, like close to assembly idea. Again, we have a problem of writing a high level code and translating it to low level, to the machine code. So they tried to come up with an idea, although it was primitive, but it helped later on in developing a more mature functional programming. This one was only limited to the JONIAC machine. It was not versatile. As I said, usually earlier versions of programming languages were computer related or machine related. They were just implemented to one machine only, the machine that is used by a certain team or a company. Then the same idea caught the attention of another team under IBM. That was at the mid of 1950s, almost same time with Fortran, beginning of Fortran. So Fortran was there actually, the initial version, premature version of Fortran. So they thought of something. Well, how about we do not create a whole programming language from zero. We make use of whatever version of Fortran available, and we create an extension of it. So that was the idea. So they worked out to provide a programming language exactly for Lisp processing, but based on Fortran itself. So they used Fortran, they extended its capability for Lisp processing, and they called this one Fortran Lisp Processing Language, FLPL. They developed, they implemented, and it was just an extension, as I said, just extension to Fortran, and it was used for proving theorems in mathematics, because we speak about somehow programming language for functional use. Okay, but that was not enough. The idea itself kept developing. Another team from MIT, led by McCarthy, designed what we call Lisp processing language. Okay, and this was initially developed based on the idea of how can we use symbolic computations in our own machine. And they started by something like differentiation of algebraic expressions. Okay, if we could realize this one, then we can do other things. And they started doing this, but they realized the idea of many missings. Missings means what? Well, we need a control structure for mathematical functions. We need some way for recursion, also conditional expression for all these structures. How about we also need some dynamic allocation of linked lists, and I'll explain why in a while. And also some way to deallocate whatever we used from the linked list after we use them. So we need some way for dynamic allocation and implicit deallocation of these. Fortran 1 for sure was not enough for this. Not at all, not even close. So there was a need for a new language. Here, Lisp came to existence. So a new language, a new format. That means we need to create a software. They started by an idea of a software to do what? Actually, to do what I said here. To try to do basic things to them, like symbolic computation. And they invented, the same team, they invented Advice Taker, which is a small software to produce symbolic computations or to do symbolic computation, and they could succeed, but it was that much small not to program with. Well, it helped in developing what we know today as Lisp, the Lisp processing language. And back then it was referred to by pure Lisp, purely functional language. All right. This Lisp is extremely popular in artificial intelligence, for artificial intelligence applications, and that's why it needed a process of data in lists, not actually arrays. And you guys should know by now the difference between a list and an array. If you don't, try to Google it. Also symbolic computation, what we referred to earlier. Rather than just numeric, we think about symbolic, exactly what we explained about logic, representation of things in mathematics. Alright, so in that case they invented, or they suggested, two data types, the atoms and the lists. Atoms, as you know, we have either symbols or numeric. Symbols are identifiers and numeric literals. And the lists, as you know, just data in the form of lists, not just atom. It's connected by some indexing scheme. The concept itself needed a linked list, and this linked list actually was available in IPL version 2. We said about the versions of IPL. We spoke about them a while ago. The information processing languages, they took like certain turns with versions until they reached the 5 or the 5th version. Now, this one, as I said, was available, so they made use of it. But what is the concept of linked list here? And let me just revise or brush up the idea. You studied in data structures for sure, linked lists. It's a way to create a list or a chained storage for data and relevant things in memory based on a beginning and an end. If we catch the beginning, we can proceed following the data in the linked list until the end. What does it mean? It means that I create a node. This is a node in a linked list, and in this node I can store some information or some data in this case, and then another link or the address of the next node, and I point to the next node. So I have a pointer for the first node. I don't have any data, just a pointer. Or I hold the address of the first node, then I keep whatever data I want in this node, and then I point to the next node. I keep whatever data I want, or list, or anything valid data type here I can provide, then another link to a new node, and so on. The final node will not be pointed to anywhere, it will be just null, and that will determine the end of your linked list. Now for Lisp, we could store two data atoms like this A. It will just point to the data itself, or another list. It will point to the beginning of the list or whatever it is in the list. Then there will be a new linked list for that list itself. So this is the beginning of another list, B. B itself, then we have BC. How do I know? Look at this. This is presented like this, just a list of A, B, C, D. If we elaborate it, now this is initially up. If we elaborate it, like if we have list of list of list, for example, certain procedure, I'll explain about it in a while. Let's say here we have an atom. This is an atom data. How do I know? Only just parentheses from outside. It's not included in any other parentheses. But here we have an inner parentheses. That means I have another list. When you have parentheses in list, means you have a list. So I have another list. We will point to the first atom data, B, then another one, C, this is its end. Again, we will have D. D itself is atom, then D is pointing to another, which is E inside an inner list. Again, E is atom, but it goes to next. Next is what? F, G, also list, and so on. So why do we do this? Usually we refer to a function that doing a process with some other functions or some other atom data. I'll explain about that in a while. All right. So, as I explained, these lists are stored in a singly linked list. This is called single linked list or singly linked list. You guys know, because we just point from one node to another, from one point to another, then we don't turn, or we don't have a back pointing or back addressing. This is called singly linked list or single linked list. It's up to you, the way you call it. So we use pointers to do that. I explain about them. I explain about all the details. Now for those we call sublists here. We have the main list outside, then we have sublists, and that's possible. Sublisting was possible in Lisp. That was one of the dramatical change in programming language. Why? Because this is functional process. We base everything based on functional programming, functions, applying functions to arguments or parameters passed to functions. So in that case, we don't really need assignments. We don't need variables. Rather, we need functions and just data or parameters. It limited also the use of loops. There was no exact need for loops. It needed a recursive call of functions. If you guys are also familiar from algorithms and programming time, that we can also create a repetitive process based on a recursion, or the recursive process, or the recursive call of functions or methods. So we don't have exactly loops. They are unnecessary. We eliminate them. We eliminate assignment statements and variables or whatever related to them. We can use recursive call of functions to do things for us. How about the syntax? The syntax of Lisp itself was based on something we call lambda calculus. What does it mean? It means, while I have my whole program or instruction itself is based on parentheses. So I create something parenthesized. And these, whatever parenthesized, means a list. So we deal with lists here. These lists can be viewed in two different ways. If you look at it as data, it's just a list of A, B, C, D. Just a list. But if you view it as a code, it's exactly the application of a function called A to parameters B, C, D. So we have a function that operates on these parameters. Imagine this is a square root, applies on these parameters in some way. All right. How about the evaluation of Lisp itself? The function itself was new, the pioneer in especially functional programming and artificial intelligence applications. And that's why it was actually extremely popular back then, and it remained popular even until today. There was no exact replacement for it. There was no other programming language back then to do the same what Lisp was capable of doing. Now we have other replacement, but still, yet Lisp is extremely popular, and a lot of people use it in the field of artificial intelligence. Now, one thing I would like to say, because it was really popular, dialects came from it. Dialects means some subsidiary or a smaller collection of programming capability based on Lisp itself. And for that reason, we will explain them separately. We have Scheme and we have Common Lisp came later on, mid of 70s, early of 80s. They came as a solution for this. I'll explain about it why. Nowadays we have meta language, Haskell, F#, also different other functional programming, but they are different in syntax. Now Common Lisp and also Scheme, they are based on the syntax of Lisp itself, but those are really different. We will try to give an idea about them. However, this was the pioneer in the field. So now, one thing, we don't have variables. We don't have assignments. We don't have exactly looping. We have recursion and conditional structure. So you expect a very powerful programming structure, syntax. In that case, it was popular actually, and it's still until today because of its functionality. Scheme itself was, as I said, a dialect, came in mid of 1970s. For what reason? They developed a subsidiary, or actually a dialect, from Lisp itself in a small size. A small size for what? They needed to suit specific applications based on static scoping or lexical scoping. You guys are familiar with static for scoping of variables and things. Now we don't speak exactly about variables in Lisp, but static scoping. If you forgot in, let's say, Java, go back and check how on what scoping is, and it is what is it used for. However, we will speak about lexical scoping in another separate chapter later on. And also, it added something powerful. Means what? It regarded functions as first-class entities. Means what? I could do literally everything with functions. They can be assigned to a variable. They can be processed as an argument. They can be returned from a function as a return value, so on. So in that case, this is another powerful, you can say, development for Lisp itself. All right, it was extremely small in size. That is why it was used back then, even for like early 90s or so. It was used for educational process. It was extremely fit for like educational course for functional programming, rather than just using the whole extensive package of Lisp for educational process. How about Common Lisp? And now I said about the mid of 70s, actually until the early of 80s, people have developed had developed actually back then so many dialects of Lisp, because it was popular, but these dialects were not fitting each other. If you write a code in one of the dialects that people invented from Lisp, it wouldn't exactly fit the compiler of the other, whatever Lisp was available at the first place. So because of that, they created something, they called it Common Lisp. So it connected all the features of several dialects of Lisp into one single common Lisp programming language. It was really large, complex, and it was used for industry and large applications. As I said, this one was used for educational process scheme rather than the larger package. And that was actually the purely functional programming language, just named after the way or the motivation for the creation of a common ground for all Lisp dialects. All right. Actually, this is the end of this session. We will have another step in programming languages very soon. Until then, have a good time. Goodbye.